All right, just to confirm, if you can see the slides on the screen.
Yes, sir.
Thank you. Right, so we are still in this topic, carrier transport phenomena. So let's just recap a few things before we move on. In this topic, we have the first few parts, the first three parts to be exact. We've discussed the basics or the fundamentals of charge transport. We've covered drift. We've covered diffusion. And then we've done a couple of calculations. We've discussed a couple of calculations in the examples towards the end of the slides. And today we're going to hop back in this charge transport lecture. And then we're going to move on to the next topic, which is generation and combination. So I hope you've tried the calculations that we have discussed, right, for yourself. Right, we've discussed this. Hold on. Let me just approve your friends. Right, so let's just recap. This one is wrong. It should be drift and diffusion, okay? It should be drift and diffusion. If you look at the title up there, it's diffusion and diffusion. Drift and diffusion, yeah? And you can use the very same equation, Q mu mu E or mu H and N or P times electric field, right? To calculate the current density. J is for current density, or to be exact, drift current density due to electrons, or drift current density due to holes, right? You just have to swap the mu and swap the electron or hole concentration in these two equations. On the other hand, if you want to do the calculations for current density, a diffusion current density due to electrons or due to holes, you have to use the below equations, yeah? Q, D, D, and dx, uh, or that D is dE for a diffusivity of electrons, or on the other hand, for holes, negative Q, dH, dP dx, right? So, and diffusion depends on the presence of concentration gradient between two neighboring regions, okay? So these are the calculations. try the calculation for yourself. The answers are already given, right? So this is Einstein relation, for example, we discussed before the break. So now let's cover Hall effect. So what is Hall effect? So is anyone working on Hall effect in order to do your FYP? Anyone working on Hall effect? Hall effect system in NOLAB? Ada ke? Buat project related to Hall effect, or you have to do some measurement using Hall effect? Any projects? No? Tak ada? Perhaps not. Okay, so what is Hall effect? So Hall effect is, if you like, it's a mechanism, but physically, it's also an equipment that you can use for the measurement of electrical properties of a semiconductor material or a semiconductor device, right? So you use it to characterize electrical properties of semiconductor material or a semiconductor device. So Hall effect is a consequence of the forces that are exerted on moving charges by electric field and magnetic fields. So it's a forces exerted on moving charges, right? So in this case, if you talk about electrons or holes as your moving charges in your semiconductor material, then there'll be forces acting on those carriers, right? Electrons are held by electric field and magnetic field. So we use Hall effect to determine whether your semiconductor material is p-type or n-type, for example. This is one type of application. Okay, so Hall effect, remember, it's also an equipment, right? It's also an equipment that we have in our lab. So anyone pernah masuk ke uh, no lab in the room where you have AFM, UV visible? Ada ke? Pernah masuk? That small space, I think close to the center of the lab. Pernah masuk AFM or UV vis room? Tak pernah. So if you enter no lab through the main entrance and then you go to the right. Okay, you dah masuk main entrance, you go to the right, then you'll see a control room on the right. You go further and you're gonna see a sputtering electron beam on the left. And then you go further, you're gonna see a one room on the left, right? So that room uh, houses AFM, atomic force microscope, houses UVV spectroscopy, UVV near infrared spectrophotometer, right? And also Hall effect. Okay, Hall effect ada dekat corner if you enter the lab, right? So this is the Hall effect that we're talking about. So the Hall effect machine or equipment, we use it for determining whether your semiconductor material is p-type or n-type. So that is one. So determine whether your material is p-type or n-type, and to measure the majority carrier concentration, and mobility. Okay. For example, if you grow, I think some of you working on zinc oxide, right? For example, or some perhaps working on silicon, or perhaps some of the materials that you grow. And it is a semiconductor material that you might not know whether it's p-type or n-type to begin with. For example, you grow your let me just say zinc oxide, for example, right? You grow by, say, sputtering, or say chemical bath deposition, CBD, or some other available processes, but you don't know whether it's p-type or n-type. So you have to go to Hall effect in order to determine the polarity of your majority carriers. Majority carriers. Okay. So Hall effect device is used to experimentally measure semiconductor properties. So these properties, p-type or n-type, majority carriers, majority carrier mobility, all of these are called electrical properties. Electrical properties, huh? So when you work on your FYP, you will probably be working on a couple of different properties of your materials or devices. The most common ones are surface morphological properties, where you need to investigate the properties of your surface, of say, of your zinc oxide, for example. So in that case, you can use AFM or SEM. You can also do a structural characterization, perhaps by Raman or XRD, X-ray diffraction. You can also use optical properties characterization, for example, by UV-Vis spectrometer. You can also do electrical properties, for example, by Hall effect, by 4-point probe, by IV characterizations. So these are all different characterizations that we typically do on our semiconductor materials or devices in order to understand the behavior or the properties of the materials or the devices that you're working on, right? So Hall effect is also used extensively in engineering application as a magnetic probe or in other circuit applications. So among other applications, right? So how does it work? So this is pretty much how it works. The Hall effect, you can see from here. Magnetic field B, you can see from all this diagram, is applied perpendicular to the direction in which the holes drift. For example, if this is if you're talking about a holes drift, then are we talking about a p-type or an n-type semiconductor? So you're having a hole drift, okay? Kenapa, Bala? Why is it P-type? Kenapa, Zuki? Why is it P-type? Why are we talking about P-type here? When you're trying to understand, right? Because holes are the majority carriers. Go back to this. Majority carriers, huh? You want to know the electrical properties of your semiconductor materials, uh, in which you have a specific majority carriers in your materials or in your devices, whether holes or electrons. So in this case, we're talking about holes. As an example, it can also be electron. Okay, so if you're talking about electron drift, then we're talking about n-type. Okay, so this is, for example, your semiconductor slab. So it can be silicon, gallium arsenide, gallium nitride, cadmium telluride, and some other semiconductor materials that you can work on, right? So then you apply the magnetic field, right? The one in the blue arrows, okay? In perpendicular to the direction of electric field, which follows the direction of your current flow, right? So these are the forces generated uh, through the semiconductor slab, and there are few parameters that you have to uh, understand, right, in order to understand the properties of your semiconductor material, for example. Okay, so the parameters listed are already listed on this page. Okay, for example, if you have you'll be getting a p-type, a positive Hall. So that means you are getting showing a p-type majority carriers or a p-type material. On the other hand, if you have a negative Hall voltage generated from the characterization, that then you know that your semiconductor is n-type. Okay. So anyone working on zinc oxide, so is it usually n-type or p-type, for example? All right, n-type. Zuki, your FYP is on zinc oxide. Okay then. Right. So zinc oxide is naturally n-type. Naturally n-type, right? So you can, when I say it's a naturally n-type, so when you grow your zinc oxide, it's typically n-type, right? But you can still incorporate dopants in order to improve conductivity of your zinc oxide. So then, um, so we used to discuss, when we talk about naturally occurring semiconductor, it used to be intrinsic. But in some cases, for example, like this, it's naturally n-type. So it's already n-type, so it's not intrinsic. So, but still, you can dope aluminium, for example, aluminium into zinc oxide to make it more n-type, to increase conductivity, to reduce resistivity, right? You can do that. Zuki, do you work on doping as well, or just natural zinc oxide that you grow? Okay, no. So just how do you get your zinc oxide? Did you do any process? CBD, right? Chemical bath deposition, liquid base, in order to grow your zinc oxide. Do you know the thickness of your zinc oxide? How thick? Do you characterize the thickness as
So
well? Yep.
because the CBD is a laser assisted CBD, so it is not like the whole pieces of the glass. It's like a micro spot. So I don't know how thick is it.
Right. So laser assisted CBD. Okay. All right. So you use you shine laser on the sample, right?
Yeah. So normally we measure the area of the zinc oxide instead of the thickness.
Okay. All right then. Okay. So there are few examples or few parameters that you can you can get from your Hall effect characterization. For example, Hall coefficient, carrier concentration, resistivity, mobility. These are all the equations used in order to come out with your carrier concentration on the display, resistivity, mobility. What you normally see is the results, right? Mobility, for example, you are getting 150 cm squared per volt second, for example, or you're getting concentration of 1 times 10 to the 19, for example. So these are all the fundamental or the underlying equations behind in order to produce your figures, okay? So to be able to run a Hall effect, for example, if you have a sample, say if you have a square shaped sample, katalah ni you punya sample lah, this could be zinc oxide or silicon or indium phosphide, whatever. Say this is 1 by 1 centimeter squared. So in order to do Hall effect, you have to incorporate metal contacts on the semiconductor. Okay. For example, okay, this is top view that I sketched here is a top view. If you look at this sample from the side, from the cross section, dari tepi ya. For example, this is the top view of this sample, my sticky notes. Kalau kita tengok from the side, so it's gonna be like that, right? From the side, it's gonna be like that cross section. So I'm just gonna sketch here like that, right? So in order for you to do Hall effect on this sample, you cannot just put the probes on this sample and expect results. You need to incorporate metal contacts on the sample in order for you to inject uh, the in order for you to run the characterization. So typically, if you have a square sample like this, you need to say evaporate, or you need to incorporate the metal contacts on the sides, on the edges of the sample. For example, katalah you ada your semiconductor here is silicon, assuming this is silicon, so you might want to evaporate or use some other processor like sputtering. So you're going to learn this in more detail in oh, hold on. Can you still see my slides? Tadi slide lari kejap. Can you still?
Yes, doctor, can see.
Yeah? Okay,
Can
good,
see.
right. Sorry for that. Okay, so you need to incorporate the contacts on the side. For example, if this is silicon, so you normally use either aluminum contacts or silver contacts. Okay, so these contacts can be deposited on the silicon by, say, sputtering process, evaporation, or some other processes. But the rule is you have to have these contacts on the edges. Then you bring the sample with the contacts on to the Hall effect machine, and then there'll be probes. So later on, I'll share on YouTube, on eLearn, uh, how does a Hall effect measurement works, right? So there'll be 4 probes. Katalah ni probe ada 4 needle. So the probes will be probing on the sample, dekat metal contact, and then you're gonna run the Hall effect measurement. And then you're gonna get your resistivity, carrier concentration, p-type, n-type, and all the stuff, right? So these are the contact design. Okay, these are the contact designs. If your contact is not if your contact is not like that, then it will not be giving you accurate results. It will still measure the properties from the sample, but then it will not be giving you accurate results. So you may not get the results expected. Okay. So this is just a calculation that you can use. You can try in order to understand the measurement. For example, you can just go back to the previous equation and see a 1-1 calculation, for example. So if you're working on, say, a semiconductor slab of 0.1 cm, Let me improve your friend. 0.1 cm with a width of 0.01 cm and the thickness of 10 to the power of minus 3 cm, right? So you can also convert this into meters if you like, but you have to convert accordingly, right? So assume that your current is 1 milliamp, the voltage is 12.5 volt, and the field is 500 Gauss, or equals to 5 times 10 to the power of 2 Tesla, and the Hall voltage is negative 6.25 millivolt, for example. So determine the majority carrier concentration, mobility, given the Hall effect parameters. So you are asked to calculate the majority carrier concentration and its mobility. So two parameters need to be calculated with the given Hall effect parameters. So what you have to do is, as we discussed just now, since you are given a negative Hall voltage, that means the majority carriers in your semiconductor is N-type, then you know already that it's N-type. The negative Hall voltage implies that you're working on an N-type semiconductor material, and therefore you can use the equation with the given parameters here. You just have to replace the thickness, the width, the electron charge, and then 10 to the 5 is your thickness here, and then 6.25 is the Hall voltage, right? And then you're going to get your majority carrier concentration, which equals to 5 times 10 to the 15, right? So that means you are having electron concentration of 5 times 10 to the 15 in your semiconductor material, right? So then you are asked to calculate the mu e. Okay, you can use mu e or mu n. Either one is fine as long as you're consistent. Then replace the parameter that you get, right? And then you're gonna get your mobility to be 0.1 meter squared per volt second, right? So try to go back to this equation and try the examples. Oops, sorry. So let me just okay. So let me now move to our next topic, which is generation and recombination, with some recap of what we learned in the previous topic. Right, can you see the new slides on the screen? Okay, thanks. So now our next topic is generation and recombination. So before that, let's just recap on what we learned in the previous topic. So the question number 1, we have an N-type silicon with an ND of 10 to the 17 per centimeter cube, right? ND equals to 1 times 10 to the 17 per centimeter cube. What is the value of your N naught? Anyone? Let's recap. We've discussed this one a couple of times already in the previous class before the break. So your ND is 10 to the 17. What is the value of your N naught? Right? 10 to the 17. Okay? Your N naught is 10 to the 17 as well because N naught is equal to ND. Okay? Good. So therefore, what is your P naught? Ni is equal to 10 to the 10 per centimeter cube. Right? So P naught is 10 to the 3. Okay? So kita pakai apa? How do you get that, Zuki? What equation did you use? What is it called? Right, law of mass action, right? Law of mass action, n times p equals ns squared, right? Ns squared is 10 to the 20. So divided by 10 to the 17, you're going to get your minority as 10 to the 3, okay? So your majority is exactly your ND or your NA, right? So second question, what is drift? What is drift? Anyone? Can unmute yourself? So we're going to use a lot of this in our next topic.
Doctor, is it movement of majority charge carrier due to the external electric field?
Yep, okay, movement of carriers due to presence of electric field, right? So that is drift. So how do we calculate drift current density? How do you summarize drift current density as an equation? Sofiyuddin, boleh unmute Sofiyuddin? Dengar suara Sofiyuddin? Can you unmute yourself? What is drift current density by equation? J equals to Sofiyuddin? Sofiyuddin ada? Are you here? Tak ada ke? Azam, can you summarize current density by an equation? Azam? Tak ada juga. Not here. Ravin. Ravin, can you summarize the equation? Not sure. Okay, not sure. Okay. Alright. Siapa yang sure? Who knows? We just learned 5 minutes ago. We just go through the equation. We just went through the equation a couple minutes ago, right?
Doctor, is it the conductivity? The relationship is like proportional to conductivity times the electric field?
Yes, but can you expand a bit the conductivity? Expand the term, the sigma equals to.
Sigma equals to the mobile density times the concentration of the electron plus the whole mobile density times the concentration of hole times the external electric field.
All right. Okay. So if you are asked to summarize the total, then you need to give the both components. Yeah. So NQ mu J equals to NQ mu times E, and your NQ mu will be from the contribution of electrons, where you have to change your mu to mu E, and then your concentration to N, and then the holes will be mu H times the P, right? Change the NQ mu using the concentration of your holes, right? So it'll be contributed by both components depending on the carrier concentration, of course. So next, what is diffusion? Okay, Fatul, diffusion is movement of carriers, electrical charges due to concentration gradient, right? Good. So how do we then calculate diffusion current density? Betul? Sama aja konsepnya, just like what I mentioned now. It will be the summation of both, depending on the concentration, of course. But using which equation? J equals to? Anyone? Yeah, thank you. So QD dpdx D in this case will be QD, DP or DH, right? Or it's gonna be QDE, DN, DX, okay, ataupun DN, right? Either one is fine, E or N, P or H. Yeah, as long as you use the substrate consistently, right? And don't forget the negative component in the front. Okay. Yes, yes, yes. You have a negative, right? So what is the purpose of using Hall effect? Final question. Why do we use Hall effect? What is it for? Why Hall effect? What properties are we trying to measure or we are trying to characterize? To determine whether the sample is N-type or P-type, yes. To differentiate P-type N-type, yes. Lagi? Apa lagi? What else can you get? Shazani, yes. Yep. To measure carrier density, magnetic field. Yep. So all in all, in essence, you want to use Hall effect to measure apa properties of the semiconductor. What properties? All in essence, electrical properties. Okay. Electrical properties, which you mentioned already. Okay. Whether it's p-type or n-type, you want to know whether what is the level of n concentration or p concentration. And then you want to know the mu e or mu h, the mobility of your carriers, your dominant or your majority carriers, right? So you can tell by looking at the Hall voltage, or you can use the equation and plug in all the fields information, the slab dimension, and all the stuff, the current, the voltage, and then you're gonna get your carrier concentration and all. Okay. So in this topic, we're gonna learn about generation and recombination. So generation here means generation of carriers. Kita nak generate carriers. How do we generate carriers in your semiconductor materials? How do we generate carriers in your semiconductor devices? And what happens after generation process? So that process is called recombination. That will normally happen almost instantaneously, right? You won't realize and they already recombine. The recombination of carriers simply means the carriers recombining with each other. They combine and annihilate each other, right? They are gone from the system. So we're going to look into thermal equilibrium and steady state concepts, and we're going to look at thermal equilibrium in intrinsic semiconductor, in n-type semiconductor, in p-type semiconductor, and excess carriers. How do we generate excess carriers? So which means the carriers that you are going to introduce on top of your thermal equilibrium carriers, right? The moment your semiconductor materials are at thermal equilibrium condition, then you introduce new set of carriers, new volume of carriers into the system. This is what we call excess carriers. Then we're going to learn the concept of generation and combination, carrier injection. We're going to look at a couple of important equations around this concept, right? A key constant relationship and parallel current. Okay, so let's understand and let's distinguish the concept of thermal equilibrium and steady state. So what is thermal equilibrium? The temperature or thermal energy of the system, for example, solar cell or some other devices, is constant with time and the same for all classes of particles, electrons and holes in this case. So there are no external agents, for example, voltage or light or fields, electric field, acting on the system. So if your semiconductor is placed in this condition where your temperature is constant with time, but there's no external agents acting on the system, whether the external agents are voltage or light or electric field or magnetic field, the system or your semiconductor is set to be at thermal equilibrium. Okay. So imagine this is your silicon, for example, and those are your carriers inside the silicon. All particles in the box have the same temperature or thermal energy. So particles in this case are referring to your carriers, right? So in this particular condition, your semiconductor material is said to be at thermal equilibrium, right? On the other hand, there's a different concept that's called steady state. So this one is a more general state where external agents like voltage or light or electric fields or magnetic field can act on the system, solar cell or LEDs or some other devices. But the properties of the system, that is the thermal energy, are constant with time. Or your voltage, your light acting on the system are always consistent with time. Okay, so in this case, the thermal energy of the electrons and holes can differ from each other but do not change with time. So even though within the system the carriers may have a slightly different thermal energy, but as time goes on, they don't have any difference in terms of the energy possessed, right? So in this condition, your semiconductor material is said to be at steady state condition. Maksudnya you can apply light. For example, you ada silicon and the silicon can be under uh, light illumination. For example, kalau saya letak silicon in my office, I turn on the light. So the light is acting on the silicon and I don't turn on or off the light uh, continuously. Maknanya saya tak buat any switching, I just leave it like that. So the system is set to be at steady state condition, right? So thermal equilibrium is a type of steady state. Thermal equilibrium is a type of steady state, but not vice versa, right? Thermal equilibrium is one type of steady state, but steady state is not thermal equilibrium. So that's what it means, right? So can you differentiate now between these two conditions, thermal equilibrium condition and steady state? If you don't have any external agents acting on the system, your system or your semiconductor material is said to be at thermal equilibrium condition. But if you have external agents like voltage or lights or some other external agent, external factors acting on the system, but it's not changing with time, so the system or the semiconductor material is said to be in steady state condition, right? So let's recall what we've learned in the previous topic. Remember last time we talked about density of states, density of free electrons, density of free holes, and we have already learned about these equations, right? Recall the equation for the thermally generated N naught and P naught in a pure or intrinsic semiconductor, SC semiconductor. And this is in intrinsic. Okay, so what is intrinsic semiconductor? What is intrinsic? Pure. Right, undoped, right? Pure, undoped. Good. So these are the two equations that we're going to use a lot when you deal with N or P calculations, right? So we've gone through the discussion of probability of occupation of states, which is essentially Fermi-Dirac distribution function, right? Remember last time we talked about Fermi-Dirac distribution function, the probability, and then density of free electrons or free holes as given here, which is the product of density of states in the conduction band for electrons times probability of occupation of electrons in the conduction band at that particular energy level. Or you can also calculate the P, which is essentially the product of density of states of hole in the valence band times probability of occupation of holes in the valence band at that particular energy level, right? So the electrons and holes are in thermal equilibrium with the semiconductor lattice. Okay, in intrinsic semiconductor, that is, all of them are at the same temperature. So the law of mass action can be said to hold for intrinsic semiconductors at thermal equilibrium, which goes back to n times p equals to ns squared. And you can just times these two together, right, to be able to get nc nv exponential of negative eg over kt, or also equals to ni squared. On the other hand, if you talk about extrinsic semiconductor, tadi intrinsic, now we're talking about extrinsic n-type. Okay, for doped semiconductors, for example, n-type, where n naught is equal to nd, okay, n naught is equal to nd, you can tell by looking at this, and you have a very small portion of p, so that means this is your majority carriers, electrons, while the whole is your minority carriers. Then you can tell already that it is an n-type semiconductor. The population of free electrons increases due to the doping, for example, shifting the probability of occupation to higher energies. And your n can be approximated to be equal to nd, and you still use the very same equation, nc exponential of ef minus ec over kt, right? So again, the electrons and holes are in thermal equilibrium with the lattice that is at the same temperature, and you still use the same equation. The law of mass action holds for all semiconductors at thermal equilibrium. Same equation, np squared. It's more of a revision, more or less, because we've learned this one a lot already. Where the subscript not denotes the thermal equilibrium case. So when you see not here, okay, the funny you're gonna see this one a lot. Np not. You have to calculate np naught, and you have to calculate the np. You have to calculate the pn naught. You have to calculate the pn. Right. Next, when we talk about pn junction in the next topic, so the naught here refers to thermal equilibrium. You have to embed this in your mind. Not thermal equilibrium. Right, which is the original condition. On the other hand, for p-type, it's just the inverse of n-type. Okay, we've talked about this quite a lot already. So when you dope your semiconductor to p-type, you can approximate your p naught to be equals to na, right? P equals to na, and you use the same equation there, p equals to na, which equals to nv exponential of ev minus ef over kt. You can tell already by looking at this. You know that in this case, your holes are the majority carriers, and your semiconductor is p-type, and your electron is the minority carriers, right? So for Na of 1016, calculate the Fermi energy with respect to the valence band. Well, you can do the calculation based on the Fermi Dirac distribution function and the density of free electrons and free holes equation. So you can do this calculation accordingly. Calculate the Fermi energy, for example, with respect to the valence band energy, EV, the population of free electrons in free holes for silicon. Okay, can use this equation. We use this one a lot already, right? In fact, when we talk about the recaps now, we essentially discuss the very same thing, right? P naught or n naught equals to 1017, and therefore your minority will be 10 to the 3 for silicon, right? So at thermal equilibrium, the net generation and recombination of charge carriers is 0. So at thermal equilibrium, the magnitude of generation and the magnitude of recombination is exactly the same, right? So R equals to G, right? Thermal equilibrium. And therefore, when R is equal to G, or you can say G equals to R, sama aja. G is for generation, R is for recombination. How much carriers do you generate equals to how many carriers recombine, okay? Because they are at thermal equilibrium anyway, right? So the recombination rate is proportional to the carrier population and equal to generation rate. So G equals to R. Therefore, R minus G equals to 0. And you can tell by looking at this, right? So whatever you generate means the carrier that is excited into your conduction band. Generation means generating free electrons from VB to CB. So this is generation process. On the other hand, recombination is just the inverse of this process, which is involving carriers dropping back to VB and recombine with whole and annihilated, right? Recombination rate is proportional to the carrier population. So that means the more carriers you have in the system, the more recombination rate is. Okay. And this is equal to G. And R can also be calculated by using this equation. Beta times N naught times P naught. Right. So which means your recombination and generation is proportional to N naught and P naught. And this is only a constant in front, right? For good quality intrinsic silicon, the thermal generation rate is typically around 10 to the 13 per centimeter cube per second and can vary over many orders of magnitude up to 1017 per centimeter cube per second for poor quality polycrystalline materials, right? So that's just a guideline, right? A guideline. But you really have to go to the specifics of your material. For example, your p-type or n-type, good quality, bad quality, and then only you can get the generation rate and combination rate. Right. How do you then generate excess carriers? So excess carriers means you already have your carriers at thermal equilibrium. Kita dah ada carrier at thermal equilibrium. Sekarang we want to generate excess new carriers into the system. You want to add more carriers into your existing carriers. So that's what it means by generating excess carriers. Excess carriers is in excess of thermal equilibrium values. So on top of thermal equilibrium values. How do we create excess carriers? So there are many ways to do that. For example, if you talk about solar cell, then of course you're talking about optical excitation. So that means you use your silicon and then you shine the silicon with irradiation under light condition. It can be the sun, it can be indoor lights, it can be many different light sources to be able to generate excess carriers, right? You can also generate excess carriers by using electron bombardment. You can use high energy system to bombard electrons with high energy on your silicon, on your whatever semiconductor material to be able to generate new carriers on top of your thermal equilibrium carriers, right? Then you can also generate excess carriers by doping, or we call it carrier injection. So we've discussed this one a lot already, right? Last time. So you can dope your silicon in this case to make it more p-type, to make it more n-type, and making the silicon more p-type or n-type itself is generation of excess carriers. Okay, so you are skewing the distribution of your majority carriers to one side, either to n-type, right? You are generating more and more density of free electrons, or to p-type, generating more and more of holes by doping, for example. So let me just go through this concept for the next two slides. Then I'll stop here. So for example, if you're talking about generating excess carriers in n-type semiconductors, so let's just see this slide, for example. An additional carrier density that's called excess carrier can be generated by external effects such as light or carrier injection. Okay, so recall that when you talk about thermal equilibrium, your n times p is equal to ni squared. Okay, thermal equilibrium condition. However, when you talk about excess carriers, you are skewing the majority carriers to one side. Either you have more holes or more electrons. And that makes your NP to be more than Ni squared. Okay, N times P is now more than Ni squared. This is away from thermal equilibrium condition, but still in steady state. So let's recall. What do you have to have in order to have a steady state condition? What conditions need to be met in order for us to have a steady state condition? Anyone? How to make sure your semiconductor is in steady state condition? Okay, Bala said properties don't change. Elaborate a bit, Bala. Don't change. What do you mean by that? Zul said external agent act on the system. Tak habis tu. Both of your answers are there, but it's not complete. Don't change. Blah blah blah. External agent acting on the system, but kena ada apa kat belakang tu? Both of your answers need the same elaboration at the back. You can only say that your semiconductor material is in steady state condition if your external agents acting on the system, but so you want to add that? You can have external agents acting on the system, but constant with time. Yes. Kena habis Kalau jawab tak habis tadi tu, dia tak cukup it's not complete. Because you may have external agents acting on the system, but with varying levels as time goes on. And that is not a steady state condition because there is variation in the level of external agents acting on the system, acting on semiconductor. So yeah, so you need time to be constant, right? Yes, thermal energy doesn't change. So in this case, it's far away from thermal equilibrium, but in steady state condition. And let's look at this. When you have excess carriers in N-type semiconductors, kita tengok if you have ND, N equals to ND, you are talking about N-type. You're talking about N-type. Let's say your N is equal to ND, and your ND is about 10 to the 17. Example. Okay. And then the moment you shine the light, for example, you have a semiconductor slab, silicon, for example, you shine the light, and the moment you have your light shown on the semiconductor, you are going to generate delta N, new delta N, and new delta P. So remember your N naught and P naught is based on which condition? This naught is what? What is this naught? Your original condition is based on N naught and P naught. What is this naught?
Thermal equilibrium.
Thermal equilibrium, right? So your original condition is your N equals to N naught equals to ND. And your N naught is your thermal equilibrium condition. And the moment you are introducing excess carriers, you are actually introducing delta N and delta P. Okay, so the moment you introduce delta N and delta P, the delta N and delta P will be of the same magnitude. Maksudnya the moment you generate new electrons excited into the conduction band, you're also generating holes in the valence band. So that means your delta N is equal to delta P. So your delta N and delta P is equal, right? So if you plug into this equation, your new N here will be new, your new condition, excess carriers, concentration of your excess carriers, concentration of your new carriers, which is a contribution from your excess carriers plus your original thermal equilibrium condition. So let's see if let's assume if your delta N is 10 to the 12. Let's do some math here, right? Delta N is 10 to the 12, assume. Therefore, delta P is 10 to the 12. So you are generating excess carriers of 10 to the 12. Oh, almost 11. Let me finish this slide. 10 to the 12 of delta N and delta P. So what happens to your N now? Delta N is 10 to the 12. Delta, your N naught is 10 to the 15. 17, sorry, your N naught original, 10 to the 17. What's the value of your N? Your delta N is 10 to the 12. Your original condition of your N type is 10 to the 17. Let's say you start off with 10, 17, N type. So what is the new condition? What is the new concentration of your electrons in this case? Fatul, betul ke 10 to the 29? Let's do the math again. 10 to the 12 plus 10 to the 17. Come. Anyone? What do you get? Simple ini, simple math ya. 10 to the 12 from delta N plus 10 to the 17 from your original condition, thermal equilibrium. What do you get? Anyone? Okay, nak habis kelas ni. Dah pukul 11.01 lah. Let me just finish off this slide. Anyone? What's the summation of this? Come on, physics, third year students. What do you get? Betul? Are you sure 10 to the 29? Angkat kalkulator kalau tak percaya. Anyone? Come. Let's finish it off. It's not 10 to the 29. Then what is it? Bala? Come, let's finish it off in 1 minute. Dah terlebih masa ni. Come, simple maths here. 10 to the 12 plus 10 to the 17. What do we get? 10 to the 17, right? Right? 10 to the 17, isn't it? So 10 17, because 10 to the 12 is negligible to this. Because it's like point blah, 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 right? So it's too small to affect your majority carriers. So therefore, your new carrier concentration will be close to your original condition, which is ND or N naught. If your delta N is 10 to the 12. Okay? We'll come back to this later on. However, let me just finish this off. For your minority carriers, let's do the very same thing. Your delta P is 10 to the 12. Right? Because delta N is equal to delta P. What is your P naught? If your N naught is 10, 17, what is your P naught? Go back to NP NS squared. What is your P naught? What is your original minority? Yeah, 10 to the 3, isn't it? So 10 to the 12 plus 10 to the 3, what do you get? For minority carrier. 10 to the 12, right? So what does it mean? So in N-type, electrons are majority carriers. When you have excess carriers of 10 to the 12, which is way smaller than your original carrier concentration in N-type, it will not change the carrier concentration of your majority carriers. So it stays at 10 to the 17, even though you've got your excess carriers. However, for your minority carriers, it will be changed because your minority start off with 10 to the 3 and you are introducing 10 to the 12. And your new P, your new hole concentration will be dependent on your minority carrier concentration. So let's just stop here and let's revisit this page again tomorrow, okay? So it's over time already by 3-4 minutes. I'm sorry for that. So I want you to go back and digest this page. How come it changes the majority? It changes the minority, but it doesn't change the majority. And in what conditions it can also change the majority carriers and minority carriers, right? So let's come back to this tomorrow at 4 p.m. Okay, bye-bye. Take care. Assalamualaikum. Sorry for the extra time. I'll see you again tomorrow.